Doesn't work. Yes, it does. Okay. So, good evening, everybody who's watching or will be watching later on. Just trying to figure out if everything is ready. Looks okay. So let's get this thing on the road. So my main idea for tonight, and probably it will take me a couple of sessions, is to address something that have been bothering me in Tract for quite a while, which is the problem of getting an efficient executor for activation function without having to code all of them by hand in assembly, basically. And even if it's fun, after a while it's less fun. So what I'm trying to do is I'm trying to figure out if I can design some kind of interpreter that we can use in Tract to execute this activation function and just port this interpreter in various assembly. So mostly I'm interested in the ARMv8 assembly, the one that goes into a lot of smart objects for a brand that is pretty obvious, but I will not say the name. Also Intel is also always of interest because obviously many people will want Tract to be performing well on Intel. And finally, a specific platform is interesting too. It's still an ARMv8 platform, but it's the Apple M1/M2/M1 Pro, etc. family. They are very different characteristics than ARMv8. I mean, than the smart device CPUs that ARM design. And because it has a specific chip which is more or less dedicated to matrix multiplication, but it could be interesting to see how it performs if we try to use it for activation function. So first things first, I think I need to explain what are the activation function, specifically because I'm going to use a more strict definition of what is usually seen as an activation function. So in a neural network, an activation function is something that is done after a big linear operation. So you have your big convolution or a big DNN layer, and on top of the layer, on top of this convolution layer, you need something which is non-linear to mimic the way neurons will fire when they reach a threshold of signal intensity. So a couple of very classical ones are these three guys. So ReLU is very simple to implement. As you can see, it's basically flat line in negative and identity in positive value. TANH is hyperbolic tangent, so trigonometric function, relatively expensive to compute because I mean, if you do it according to the definition, you'll have to go through the exponentiation and also division, which is a lot of things. A bit of the same for sigmoid. Actually, sigmoid and tangent hyperbolic are related by kind of affine relation. So if you have one, it's pretty easy to get the other one. And there are a few more here, which are often variation around ReLU. So ReLU is super easy to implement, but it's a bit too harsh for training. It has this specific thing at 0, so it's relatively violently discontinuous at 0, or not derivable at 0. plus the fact that it kills the signal in the negative part, hurts training quite a bit actually. So there are other possibilities, and I mean new ones, new activation function pop on a relatively regular basis. For instance, one that tract doesn't know how to do is swish. So that's hard switch. It's not. No, that's the one actually. That's the one I want. There is also one called swish. Hard swish and hard switch. So, well, it's not there. I thought it was in the ONNX specification, which is basically the standard that tract tries to implement. So hard switch is the one that actually one colleague of mine wants to play with and is a bit frustrated because it's not implemented yet. And there is also a switch function somewhere, but it looks like it's not part of ONNX. So among this incredibly big list of operators, there are activation functions like that, and first, I will try to figure out some of the characteristics of them. So let's try to do these, and I'm gonna do side things. Okay, and I want to go to Kali/coding. Here we go. Ah, great. Okay. Up moves the only to a new window, and yes, that's what I wanted. Okay. So you can only see the left on the screen because of the chat and stuff. So let me get a bit more room up. Something like that. Chat is empty really, but who knows? First time I stream, I had 200 people, 20 minutes in the stream because there was a raid. So you never know. Anyway, that's the right page. So what, except the fact that it's nonlinear, what do I want to define as an activation function? I want functions which are element-wise. So every output, every value in the output tensor is the result of a function of the input tensor and one single value. So basically you iterate over all the values in the tensor and execute a single mathematic function. So actually all of these apps would fit the bill, ACOS and ACOS H, so that's arc cosinus, arc, what's the name? Hyperbolic cosinus, but these are not super interesting for neural net. Same for these two. The first one, let me try to start editing this. Okay. So we are focusing on element-wise operation. Element-wise. So result tensor is how to say that simply. So output equal for x in input f of x. Yeah, so the idea is really we are just looking at these f function which takes one value and return one value. We are interested in operation which are also, I mean, it's pretty obvious here, but result is independent of geometry. So it doesn't matter on which row, on which column, or whatever, on which dimension we are computing the value. It has to be the same function everywhere of tensor geometry. Because some of these activation functions are actually element-wise. Some of them have dependency on parameters which are dependent on the row or the column of the tensor. So we only accept, let's say, scalar operations. No broadcasting of tensors and stuff. Okay, so with this we had we had a couple of them. Nope. Activation. So we have these three guys. So at this stage, I want to also say which one are implemented and how in tract. So these one are actually implemented in assembly on most architecture, most major architectures. So let's say ARMv8, ARMv8, ARMv7, Intel. So Intel is Intel FMA, and tract implementation. And I mean, it's okay, but it's a bit cumbersome to maintain them. I mean, good thing is they do not change very often, but sometimes there is a new one. Like recently, people started using ARMv8, which is one more of this function which has always the same kind of S shape, and ARMv8 is subtly different from these ones. It doesn't have a definition. Even if you already have an exponentiation, you cannot express ARMv8 like that. So you need some approximation. But anyway, we're not using these exact mathematical definition. These functions are implemented as rational approximation. So rational approximation is a polynomial of x divided by a polynomial of another polynomial of q. And these polynomial and division operation are implemented in assembly with the right coefficient and stuff. So I don't know if I will go as far as supporting these scenario. Support rational function evaluation, because we already have something for this, even if it's a bit manual, and it repeats itself, because we have hyperbolic tangent for ARMv8, hyperbolic tangent for Intel, and we actually have several of them for ARMv8 because of trade-off depending on the machine, on the actual CPU, because ARMv8 is a family. So all of these mean that maybe we could factorize all of these rational approximations into one single bit of assembly, which would allow to implement ARMv8 just by providing the new coefficients. So that's basically one idea. But it's a bit more complicated than some of the functions that we are going to consider. So I'm not 100% sure we want to go there. So ReLU, this one is definitely interesting for us. I mean, it's very simple, and at this point, so ReLU is re-expressed as max of 0 and x, and so this is implemented either by, in most cases, by a Rust, an iteration in Rust. And so it's unclear how this is translated into actual machine code, we could have a look, but yeah, for other reasons, it's I mean, I still want to do it, even if Rust does a pretty good job at inlining the loop, and I mean inlining the loop, vectorizing the loop, which I'm not sure it does. I'm still interested in having an actual implementation in assembly. We also have a fused assembly implementation. So if we are doing a big linear operation, if ReLU follows a linear operation, which it usually does, it is fused with the linear op, which is a good thing, because basically this will take like one cycle or even half a cycle to do over, let's say, on ARM8 over 4 values, or 8 values if we are dealing with half precision, and so the fact that it's fused with the end of the linear matrix multiplication means that we will not have to go back to the memory, push the result of the matrix multiplication into memory, and then fetch it back, do the max, and then push it back to memory. So we are saving a lot of memory exchanges. Okay, so ReLU is, we have something which is half satisfactory already in Rust with the fused implementation. Then so we have these guys, which are not actually, this is not the list of activation function in ONNX. It's the list of activation functions that can be used in the context of LSTM. So the two lists are a bit, I mean, they are entirely different. So we are not going to look too much into this one, even if a couple of them, at least we'll write the name. Let's say that we have from LSTM, we have ILU, we have, I'm not sure why I started there. LSTM, affine, leaky ReLU, threshold ReLU. So all of these are really variation around ReLU and very simple function. So in that case, leaky is same thing as ReLU, plus we have a lower slope in the x. Instead of being just at 0, we are actually still linear in the negative space. Threshold ReLU is if x over alpha. Okay, so it's just an offset ReLU. We have scale tan h. So that's one is, well, it's scale tan h. We have the hard sigmoid. So the hard sigmoid is affine plus min and max. So some of these are relatively easy to compute. Like this one is easy, this one is easy, that one is easy, that one is easy. This one is expensive because we have to go through a rational approximation. That one is expensive because it requires an exponentiation. ILU, soft sign as an absolute and a division, so it's somewhere in the middle. And soft plus is super expensive because it has log and exponentiation. So now let's see. We have more. Actually, I will put I will put some definition because I need them somewhere. So affine is alpha x plus beta. Okay, alpha x plus beta. Leaky ReLU is if x positive, then it's x. Definition in the Python way, don't like it. Alpha x threshold equals if x bigger than alpha, then x else 0. So that's the threshold ReLU. Then we have scale tanch, which is alpha times tan h of beta x. So actually sigmoid is probably a variant of scale tan h with the right alpha and betas. Note that it's super important, but hard sigmoid is mean of max, so it's a clamp of alpha times x plus beta and locked at 0 and 1. So that's that would be S, but with segments. Then we have something called soft sine, which I'm not sure what it looks like, but at least it's not too complicated to compute. 1 plus absolute of x. And we have soft plus, which is soft plus is, so that one is tricky, log of 1 plus ex. Okay, so that is done. And then what else do we have? We have, let's look at, yeah, so we have also other things which could be interesting. I mean, I'm curious about this one. It's not actually an activation function, but if our interpreter can compute some of these, and I'm thinking tan h and sigmoid, for instance, maybe we can use it to implement efficiently the one of the fast exponentiation algorithm that are around. Can we make a faster exp? What about log? Okay. And we have more. So if I look at element-wise function, so absolute, I mean it's not exactly an activation function. It could be in some word space. So sail, we haven't seen, I mean, it's not an activation function. It's not a primitive of computation for these, but actually sail and flow plays a role in computing some algorithm for fast exponentiation. I saw something called CLU, continuously differentiable exponential linear unit, performs the linear unit element-wise. Oh yeah, so I was looking for element-wise pair like that, but it also appears with a dash on the input tensor x using the formula. So we have an exponentiation here. That one is tricky. Okay, let's add it to the mix. CLU is max 0x plus min 0 alpha times exp of x alpha minus 1. And that's not right yet. Alpha times Yeah, okay, it's good. Yeah. This thing is starting to be a bit of a bother. Okay. Then let's keep looking at element-wise. A spell like this. Ilu, we already have it. No, nope. I forgot it, I think. Ilu. So Ilu is it looks a bit like Silu, but it's different. So Ilu equals if x negative, it's alpha times x minus 1, else it's x. Okay. Next. So once again, exponentiation and even exponentiation minus 1, which usually it's interesting to have a specific implementation for exponentiation of x minus 1 because around 0, exponentiation x minus 1 will be around 0. So we could, with a specific function, we could have a higher precision because the floats are denser around 0 than around 1. So if we go through the usual exponentiation and then subtract 1, we lose the extra precision that the float have at 0. Floor is interesting not as as I was saying, not as an activation function per se, but it's interesting as a primitive to compute some of these functions. And then we also have what else? My mouse doesn't want to come back. Okay, element-wise. Next, greater. That's not an activation function. Art sigmoid. Okay, this one I already have it. Next, art swish. That's the one my colleague wants. It's actually a very simple one. It was designed to be simple. So it's x time max of 0, min of 1, alpha x plus beta with alpha with fixed values and beta. Okay. Next. Liquid relu. Liquid relu already listed. Okay. Less or equal, negative, same. It's again, it's probably something that we will need as a primitive, but not necessarily as an activation function. Or is a binary operator. Prelu. This one is not an activation function in my current definition because the alpha is called slope here, and it's a tensor, and it's not a scalar. So every, I mean, if you apply a prelu on the result of fully connected layer or convolution layer, every channel in the output will have a different slope. So this, at least for now, and probably for a bit of time, is not in the scope of what I'm trying to do tonight. Element-wise, POW, reciprocal, same. So reciprocal is probably a primitive that we will need, but not an activation function. Relu is max of 0 and x. Silu takes one input data and produce one output data, whereas a scale exponentiation linear unit function. Okay, so it's one more with exponentiation. So that's Silu, and it's equal to gamma time alpha times exponentiation minus alpha, and this is for x negative. and gamma times x for x positive. Okay, that's one more. Sigmoid already discussed. Soft plus already there. Square root probably not even obvious actually. Nothing seems to be using it. The funny thing is that it's actually something that the CPUs know how to do, but we are not using it anywhere apparently. I mean, we're using it in neural network. There are a couple of times when it happens. It's not that common. Threshold value already listed. I just wanted to check that we don't have a concurrent definition with a tensor like Prelude, but no, that's fine. XOR, that's binary. Okay, so that's it for element-wise spelled like that. But I still want to look at, okay, so we have the trigonometric functions and hyperbolic functions. We have the binary functions. So we'll have a lot of noise here, I guess. That's asyn h. That's asyn h again. Arctangent hyperbolic version. Again, bit shift we may need for exponentiation, but as a primitive again. Bitwise note, CLU already discussed. Cos trigonometric. So trigonometric function, it could benefit from a vectorized evaluator. Once again, I don't know exactly how good is the Rust plus LLVM compiler. That's also something I would like to try at some point in this process. But trigonometric functions are not super interesting in neural net context, except for tanh, hyperbolic tangent. Okay, cos h, division, erf. Erf. So erf is of same family than tangent and sigmoid. So I'm gonna add it there. It doesn't have a definition in terms of even exponentiation. You cannot express it. So if we want erf, we need to have an approximation of it, and it probably has to be, it certainly has to be a rational approximation. Then what else? Exponentiation. So exponential, not exponentiation. That's it again. Yeah. Logarithm, though, the opposite one. Max, binary. Min. So this one is complicated, and it's an activation function. Min. Oh, a new one. Whoa. Okay, that's a new one. I mean, good point that we did this, even if it's a bit boring for now. Mich x is x times tanh. Wow, soft plus. At least soft plus is not easy. I mean, this one is crazy, really. I hope that we don't have to optimize this one, because or alternative definition x times tanh log. I'm not sure which one is worse. I mean, it's the same. They just expanded. Soft plus something is. So here it's a log. There is something fishy here, but well, I mean, okay, yeah, there's something weird. But I guess it's okay. So if this one, I mean, exponentiation, logarithm, then tan h. I mean, if you want this one, I'm not sure what it looks like, but it probably would have to be a rational approximation again for the whole thing. I mean, it's possible that for, I don't know, for ILU, for instance, we may piggyback on the exponentiation or exponentiation minus 1 implementation, then just compute the rest with what we are designing. But for these big things, honestly, I don't know who don't know where to start. Okay, next. Window, modulo, binary multiplication, not round, okay, sin, that's again a primitive, that's sign, sin, yeah, not super interesting, sin h, same, soft sign we already have it there, and x over 1 plus absolute, yeah, that's good. Element wise, yes, sub, that's the subtraction, sum, yeah, it's a kind of multi-array addition, tangent, and then tangent hyperbolic, so hyperbolic tangent in English. Okay, and then we are somewhere else. We're in a different part of the document where there is no activation function anymore. So there is this new one, which is really it's so scary. It's scary as hell. But now if we try to, maybe I will comment this one list. Activation functions from ONNX. Okie dokie. So if we look at this list now, red, why is it red? So I'm gonna annotate. So the fusing happened for more than ReLU. It can happen for many of them actually, because the fusing will support multiplying by a constant. It will support addition of a constant. So this one would be compatible with the fusing of. With the principle of using the activation function at the tail of the matrix multiplication. Leaky ReLU, it has this if then else, and so that one at the current point is not mergeable is not fusible to the matrix multiplication. Same for this guy. No, because this is actually max of x. If x bigger than alpha, then x equals 0. No, it's a weird shape. So nope, we cannot express it easily with the max. So we have a couple which are simple ops plus if then else. All right, next one, that one is in the simple bunch. Soft sign, yes, I will consider it there, because even if we don't want absolute, we can implement absolute with an if then else. It's a bit dirty. So now we have these ones are, let's say that probably need a rational approximation. Let's just say approximation because some of them can be polynomial. Yep. Very much, yes. This one, nope, that one is the one, yeah, that's the one from my colleague. So let's have it in the easy bunch. CLU, alpha exponentiation. I mean, yeah, as soon as we have exponentiation or tan h, they are more difficult. So we'll leave them. We will leave these ones alone for now. So these ones are current state. So in tract, I mean, this function already works. Even these, I think all of these except the crazy Mish, they are already working in tract, but they are re-expressed in terms of combination of other operators. For instance, if we look at ILU, a network featuring ILU will feature an exponentiation, a node for the exponentiation, then a second node for the subtraction, plus an extra node for the constant. Then alpha will be in its own node, the multiplication will be another operator, and then we will have an operator for the test and an operator for the if then else. So that's a lot of operators, and at every one of them we will move data between the CPU and the memory, so that I mean, this operator will be made incredibly expensive. But I mean, in the end, we still have the exponentiation to compute, which in itself is expensive. But for these guys, and so these guys, nothing is very expensive. At worst, we have a division here, but most of the time this one has just two multiplications, so they are pretty fast to compute. And so doing so many exchanges between the memory and the CPU, it feels bad. I don't have hard numbers for now. Maybe we will have at some point. Maybe I will do a bench. But so basically, we have the current situation is some of these operators are just coded as I mean loop for in Rust, doing the operators on each element. I mean each element after the other, hoping that Rust will do a good job at vectorizing these, but it's not that clear. Or they are decomposed in many subparts, many sub-operations with back and forth access all over the memory at every point in time. So my idea to solve that is to design a small language, let's say, or a small VM, virtual machine, where which is dedicated to process these operator in vector style, and that we will be able to implement on various architectures. And so what I want, because I already think about it a bit, so we'll say that this, for instance, we'll assume that I'm gonna commit this up, edit. So let's assume that we have I'm going to assume that we have a virtual machine that has, let's say, 4 registers, which in the actual implementation will be made of one or several vector registers of the actual architecture. One or several hardware. For instance, I'm thinking on ARMv8. We could take 4 times 4, so 4, 1, so 1 register, maybe 4 neon registers. So that would mean 16 F32 values. And that's 4 times 4 F32 values, or 4 times 8 F16 values. So I'm not sure how to call them. Maybe big registers to distinguish from the underlying hardware registers, or virtual. I don't know yet. And so if I'm doing this, I mean, we are using 16 registers only. 16 neon registers are used, and we have 16 for housekeeping. And because if our operators are fast, then at some point we need to have some prefetch registers where we will pull data in advance to be processed at the next run. So while we are working on, let's say, 16 F32 values, computing one of these functions, and the MMU is actually filling up 4 more, or maybe twice 4 registers for the next values in the tensor. Cache. So that's a prefetch caching plus whatever we need to implement the various operators. Maybe, I mean, I'm writing here like 4, but maybe in the end it will be 6, or I don't know. I mean, just, and maybe if it's still 4, maybe here we will use 6 of them. And this is, I mean, yeah, I'm trying to figure out what we can do. The question is, can we compute all of these with 4 registers? I think the simple ones, yes, we will check that. I think also maybe the rational approximations fits on 4 registers, and that's, I just thought about it, and in my head it was working, but we need to check. And well, then there are these terrible things that really I don't know how to deal with, but that's a different story. Okay, so if I'm focusing on the simple batch, we need, so we'll assume that if we have 4 big registers, so big regs, or let's say ABCD, and so let's look at what we need in terms of operator. We have a max, we have multiply, we have plus, we have if then else, we have what? So we may want to do some kind of if pause instead of if then else, because in many cases we get compare x to 0. Here we have multiply plus, we also need min and max. So I'm gonna more or less sorting them by increasing cost. We have a division for soft sign, and we have that's all actually. And yeah, and we also have constants. We have absolute apps. and we have some constants. Okay. One other thing which is interesting is, except for this guy, for out swish. Oh no, it's true for soft-ending. I was about to say that all operators are multiplying a variable with a constant, or I mean, multiplying or doing their job on a variable and a constant, but it's not true. It's not true for this division. It's also not true for this multiplication. So maybe, so because if it had been true, then we would have had something that looks like plus or multiplication with how is it called in assembly? Literal? Don't remember. How do we call that? Yeah, I think it's literal. So an actual constant hard-coded next to the operator in the assembly, or maybe a bit farther on the file, but something really close. With these things, we could assume that framework load x into A, let's say, and expect results in A. So that's a calling convention. Except okay. And so well, ReLU will be, I'm trying to figure out what are the operators that we need. So ReLU will be something like that. These things are a bit cumbersome here. I need more real estate. Okay. So this one, they're actually working, so we don't have a problem now. It's just super inefficient. Computed from exp log and tanh, etc. as separate operators. Okay. I have an old phone next to me, which is which I'll try to charge, an old iPhone, and it's slowly dying, and it's super annoying because it's vibrating all the time. Yeah, again. Oh, I remember. It has a yeah, I think the switch toggle, the silent toggle is broken, and I remember now why I stopped using it. Anyway, sorry for that. So affine. So affine is alpha times x plus beta. So we could compute it with A gets mul of A and alpha, then A gets add of A and beta. Next one, Nikki. So Likki ReLU leaky ReLU. So we have the first x positive. So first we'll need to compute alpha x. So maybe B gets alpha mul of alpha and x, mul of alpha and A, because x is preload in A. So that's our, this is x positive, then x else, that's the negative side. Then maybe we could say that we're moving A to C. And finally, or maybe let's do it the other way. We could have if pose A, if pose B, else C operator. So I'm trying to limit a number of. I don't want to have a combinatorial explosion of operators. So even that one, I'm not super sure about it, because if I do this, then I will have, let's assume that the constant, let's try to stick to the other order. If we assume that this is multiplied by a constant that comes from someplace else, then I can perform multiplication. Because that means that I have at least one operand and one destination. So that's already 16 variations, 16 combinations. And I can generate them, but I will not write them, that's for sure. But if I'm allowing to put 2 operand registers, then it's even worse, because we get at 64 combinations, and we'll get a huge assembly file that I'm afraid will not perform super well. So I'm trying to limit, what I'm saying is I'm trying to limit the number of operators that actually have high cardinalities of registers. So I definitely don't want to do if A, then B, else C. This is something I don't want to do, because this is 64 combination. So maybe what I want is if then else with test or condition in A, then in B, else in C, and that always put the results in A. So yeah, this one is problematic. Another way is to say that we have all the moves, so the 16 moves, because we have 4 registers, and then the other operators work with fixed registers, and so we're moving stuff a bit, but it's moving between registers and registers, so it's not as crazy as moving from memory, of course. So one option is to have 16 moves ops plus and fixed Okay. Let's see where we get. Let's not worry too much about combination at this stage. Okay, so leaky. Can I somehow found a more compact way to represent these? I'm struggling with the screen space. Okay, it's not too bad. Leaky is then so result is yeah, I will worry later about how to do the combination. So if then else of okay, so let's say a so if pose a, then x is in still in a, so we have a problem. No, I don't have a problem. Else I can say I can take b. Leaky, then threshold. Relu. So for threshold relu, I have I can try to do if pose. No, it's not if pose. So I need to copy x. So I'm gonna put x in b, and then I'm doing x x is a. So in a I'm putting a minus the constant alpha, and in a I get if pose of a. So if it's positive I take b, else constant 0. So here we have a variant of if pose here with 3 operands, which I don't like. And we also have a variant with a constant. So one way is to say that we put 0 in, let's say, C, and then use the same variant. So the one that would take 3 registers, which is too much. Anyway, let's finish this. Soft sign. Soft sign would be spelled apps. So I need to move x to b. Then I can run apps. So I'm already more or less assuming that all, I mean, it's not strictly true, but most operators will write to A. Then I have A plus 1. So I have A, recip of A. Yeah. And then it's A mul A and B, or B and A. Okay. Out switch. Out switch. So in out switch, so first we can implement the clamping. So it's a max of A and 0. A is min of A and it's not spelled like that. Okay. All right. So actually, I mean, this one, it's actually some. It's actually a kind of a bit of a parable, plus a plateau at 1 on the right, and a plateau at 0 on the left. So we can actually find the right x min and x max, that and so clamping and then doing the polynomial part. Let's look at hard swish, what it looks like. Hard swish. Oh, I was wrong. No, it's not. I thought there was a cap. Yes, there is a cap because we will see is capped. It just doesn't show. I mean, it just doesn't show it there. Let's try to find another page. No, so after x, it's x plus 3. So, okay, no, it's not a plateau. Got it wrong. Okay, that's... so, yeah, okay. My idea doesn't work. It's fine. So, bloop, bloop, bloop. So we need to compute from the inside, actually. So a equals a times a mul times alpha. So like that. Then a is add a plus beta. Then we do the mean with 1. So that one actually is a run register thing. Max of 0 and and all of these go to just like that. Okay, so I never use the D register, so I could have this with 3 actually, which is nice because it reduces also the number of combinations. If we want to go with all operators, allowing all operators to read from any place and write to any place. That's option B. Can be const or any registers. So which raise to with 4 registers, with 4 big registers. Okay. But there can be, I mean, could be compromise. Could be interesting compromise in there if you want to look at it. So let's try to rewrite these with the assumption that we are choosing the all ops of fixed registers. So unary ops are A from A. Binary are doing A from A. I need a weird character. So one that I'm always writing when I don't need it, and which for once, okay, let's use this one. Binary will be this one, and ternary will be A, B, C. And okay, so if I want to do this, then I need to do B, I need to load load alpha in B. Then I need to do mul. So load B alpha. So we still have these. So mul will do what I want. Here I'm going to do load B0 max load B alpha mul, then load B beta add leaky. So I need to load alpha, and I need to move A away. Yep. So I'm going to put X in B like that. Then I'm going to load in A. I'm going to load alpha. I'm doing mul. Yes. And then so if I'm doing the simple variant, I need so it's a if pose, and so if pose we say that if pose is a ternary. So I need to put value if pose in B and value if negative in C, and I'll look at the definition here. So I'll do leaky. So value if negative is alpha X, and it has to go to C. So that's the one I have in A. So C gets A, and in B I have X, which is already there. So I think this one works. Then what else? Threshold ReLU, threshold. So we end with the if pose. We want in B we will want X, which is good. In C we want nope. Yes, in C we want. So we cannot put B in X yet because we need to put alpha in B to do the subtraction. So we are going to put X in C. We are loading alpha in B. We are doing the subtraction. So that's X minus alpha. Yes. Then so now I have in B I have alpha, and I need in B, which is the positive case, I need X, and X has been put in C. So I need to do this from C, and in C I want 0. So on top of that I will load in C, I will load 0, and then I can do the if pose. Not sure if it's right, but we'll assume it is. Next, so absolute it's like that. So I need to once again I will need to load 1 in B to do this one plus. Then recip will work from A to A, and in the end, I also need to multiply by x, which I must save somewhere. So I will save it in C because B is overridden there. And here I need to move C to B again and perform the multiplication. Finally, hard switch, if I'm choosing these operators. Load in B alpha, mul, then load in B beta, add, load, it's a lot of loads, in B A1, perform min, and load in B0 and perform max. Okay, so the good thing with this is, I mean, we have a lot of loading to B, which makes sense because most of the time we will want to make our value interact with a constant. So it's not super surprising that we find a lot of these. And we could replace them with, because here we just have, I mean, the binary operators are just one opcode, because there are no variations. They always do A plus B goes to A. Maybe we want to have some kind of maybe we want to have multiply by a constant and add a constant and be able to invoke these directly without going through the load. How does that look in assembly? I will still need to broadcast, and even in assembly it's actually interesting because if I'm doing a load on a big register, I will have to duplicate the single scalar value to several of these big registers. Instead, if I have a const, if I have a way to address a const, then I can jump directly to and even in ARM we have these. You can actually multiply a vector with a scalar. So the scalar is broadcasted across your vector, and all the vectors are multiplied by the same scalar. So we could benefit from having two variants of the binary operators. So we could we at least need the binary here once. We also need in the threshold ReLU we do subtraction between, nope, actually it's a constant, the other guy is a constant. So that's the variation with all moves. Load to load const. Load const to any reg, and unary, binary, ternary on ABC. So let's try to see what happens with binary with constants. So in that case, well, this one, and so yeah, it's like that actually. Binary. So it will always be binary A with a constant. I'm not sure to write this, but maybe A times K. Okay, so here we're doing mul alpha instead of this, and add beta. Here we're doing leaky, I forgot. Yes, that's the one. So no, alpha x in negatives. So alpha x, but I need to preserve x, so I'm putting, I'm copying x to b, then multiplying, so that's mul alpha. So this is negative, so I need to bring it over there, and assuming alpha is positive, this will not change the sign, so I can still use if pose to pick the right variant. I'm starting to wonder if we do have moves that are not with A. Threshold value, threshold. Come on, if x, this thing is very cumbersome. So let's try to move this. Okay. Okay, so leaky. If x positive, then I'm doing if x positive, I'm doing x. No, I'm lost. Leaky, I've already done. I'm on threshold now. Threshold, if x bigger than alpha, so first I need to subtract. So that's I need to load, I need to sub alpha to x. But doing this, I'm destroying A, which I will need to have put in C, or in B actually, now, because yeah, one of the benefits is that I'm no longer destroying B for these. So I can get rid of these. So I have x in B, I have alpha x in I have alpha minus I have x minus alpha, assuming that it reads left to right in A. So I can do the if pose, but to do the if pose I also need to have a 0 in C. So I guess I still need a load C0 in this specific case, but it's not too bad actually. Right, soft sign would become I need to copy X somewhere. So let's say C. I'm doing apps, I'm doing add one, I'm doing recip in place, then I'm multiplying by B, so I need it in B. Okay, it's not so bad. It's really not too bad. Hard switch. So hard switch, we're doing mul alpha plus beta and min. Yeah, I mean in this case the idea of having the binary working with constant really pays. And so also what is interesting is we managed to do all the 6 simple ones with just 3 registers. We only need C. We never use D. And so here we have moves between 2 registers, which it looks like A is always the source. Is that always true? I'm not sure. But here we have a language which is pretty compact, which is nice. We have this guy, which is a bit of an oddity now. Do we want to keep the load to any register, or do we say that loads always go through A? That would be a bit cumbersome, I guess. So yeah, we can keep the load because I'm not sure if we are going to encode this, but yeah, we can probably find a nice way to encode this. So the next step would be to now we probably want to try these with reference Rust implementation. So basically define these operators as an enum in Rust and rewrite these functions. So use the reference implementation that is there to compare them with a language like that. Assuming that we have a minimum reference implementation of the language in Rust working on Scala, because you don't need to vectorize right away. I mean, we just want to validate our language, then that's something we can do right away. And what I would like to do is maybe start with this. So taking this specification actually. We have moves between 2 registers. We have load to any register of a constant. We never load a variable, we always load constant because we are doing activation functions. Unread, binary, ternary act all on A, B, C, or just A, or just A and B. Plus, we have another variant for binary operators, which will act with a constant. And so I think that with this we can actually do the 6 operators, and I would be super happy if we get an easy way to represent the rational approximations. But let's not get ahead of ourselves. We'll just try. I think we'll just try to do this one, and maybe I will get this one out of the apps and recip will be easy anyway. Okay, let's do some Rust now. Let's save this Yes, it's GitHub, so I have a commit button somewhere. Okay. Okie dokie. So, up, going there. I haven't checked it out yet. Git clone, github.com, /Kali coding. Okay. Really? What? Yeah. Okay, so this is what we just write. And so I'm gonna do the code in tract, even if I'm not sure that this will ever be part of tract. I don't know. I don't know. We'll see. If it goes to tract, it will be in linear algebra, which is a super big misnomer, but everybody does it because, I mean, this does have linear algebra because it contains the optimized matrix multiplication. But what we are doing to do is very much nonlinear stuff by definition, because activation are the nonlinear bits in neural network. So I'm going to we don't even need to be in tract really, but I don't know how to call it activations for now. Okay, so I'm gonna start it as a separate project. So as I'm in a workspace, there is this weird thing. Message is scary on the screen, which is too small. But fix is super easy. Fix is I need to specify workspace, and I need to put an empty array members, and this should be enough to get this to work. Yep, okay. So okie dokie. So we have our ops. Ops again. I mean, there are so many things called op in tract that it's not. Yeah, it's a bit of a mess. But we will have an enum. Nope. So we said we have moves. Okay, moves from one register to another. So source will be src will be let's say usize for now. dst will be usize. So these are register ID. So let's make it nice. Register ID can be A, B, C, or D, and it will want them in caps. So source dest or dest source, I'm not sure if one is better than the other. We have loads. So yeah, for this one I really want it like that, so let's make it consistent. dst src. Okay, and so we need a constant. So problem with constant is that if I'm executing these things on F13 or F16, the constant will not be the same size. So I will use a table of constants. So we will have a constant ID, which will be usize, constant ID usize. And I think that constant ID 0 will be 0, constant ID 1 will be 1, and then the 1 will define on each operator, something like that. We'll see later. So we have the move, we have the load, we have the binary oops. So binary add, binary mule, binary min, binary max. What else? We have if, both, then else. And we have the binary show. I'm gonna just call this add mul min max and add const. So add const will take constant ID usize. I'm gonna simplify this a bit. I'm gonna define again, what is this shortcut? I'm gonna define a type constant ID as usize. And so this way I can make it a bit nicer, constant ID on the ice. So add mul min and max. Okay. Next, what we want is to translate our bit of assembly here into into assembly. So I'm going to how am I going to do that? Const. Not sure. So let's start with functions. Real will be so the state of the program. We have this constant that we have to put somewhere. So we'll have a sequence of operation plus some constants. So let's struct program, and we will have ops, and I'm not. Yeah, okay. Let's start easy. Vector of op, and we have consts key. Vector of vector of what? We will have to. Okay, let's consider that we are working with F32 for now. So Relu will build our program, and it will be made of ops will be vec of so it's gonna be max const, and we say that 0 will contain 0. And it's op. Okay, this one is pretty easy. Consts is an empty vector. All right, then affine. Affine is so alpha and beta will be constant 2 and 3. show constant, so affine will take alpha f32, beta f32, and we'll put them in the constant vector, so with the caveat that 0 and 1 are already taken. Okay, alpha, beta, hopefully it will make sense. And we do op dot affine mul of alpha. Alpha is constant number 2. And op add beta. Beta is constant number 3. What's wrong here? I've picked the wrong one. It's mul const and add const. Ensuite, later, next. Where is my mouse again? Okie dokie. Affine, leaky. Leaky relu. So leaky relu has one single parameter, it's alpha. And so the program will be move B towards A. So B is B is destination first. So BA. I will need yes. So it's register ID. B register ID A, and then we do. I'm not changing the right one. Damn. So this one is affine. Yep, I got confused here. Beta f32. So this one is affine. Alpha beta, and it's affine. So this one is leaky. So alpha and only alpha. Okay, so we're moving A to B. We are doing sub. So I need to add sub in the operators. And so alpha will be 2. And then we're loading 0 in C. Load into C. I'm loading a 0, which is constant 0. And I have a single definition of constant. So add sub. So yeah, and this means that I will soon need a neg to complement that, to be able to implement both subtraction. Subtraction in 2 directions. I mean, I think the problem with my stream really, my screen is too small. Something is weird with OBS. It looks good in OBS, but when I'm moving to the Twitch screen, it's like I only have half of it on the screen, so something is really definitely off. What? So weird. Oh no, it's back again. So it was just the UI of Twitch which was off. I still have absolutely. Oh yeah, I have 2 people following. Oh, that's good. That's 2 more than I thought. Hey guys, thanks a lot. Okay, so where was I? Leaky. So moving, moving A to B, then loading. Then I need the mule. I need a mule alpha here. Up. Mule const 2. Then I'm loading 0 in C. Yes, that's constant ID. I'm gonna make everything a tuple to make it a bit nicer, and I'm putting the constant alpha there, and I need I also need here the operator if pause then else, and I forgot it in affine. No, affine doesn't have it. Op if pause then else. It's super ugly, but okay. So let's change this so it looks a bit more like actual assembly. Up. Load constant ID is a constant ID. Okay, constant ID. So I'm going to do mode. I'm going to call these definitions. What I want to do is I want to do a submodule to put because I mean, in order for it to be nicer, I will be able to import use op super op everything to get rid of the prefix. So now I can write it like that, max const. Yep. Op. Up. There's more. Here we go. And I need basically I will also need to import everything upstairs. Okay. So load now is spelled so I will also use that. This was the point really. I can use this, so I can write load C 0. So much nicer. Move B to A. I'm not sure I like it. I'm not sure I like it like that. Okay. Mul const 2 at const 3. This one is actually okay. And it's not too bad. At some point, it's, I mean, if I'm starting to use this a lot, probably some macros can help writing these functions. Leaky threshold. So threshold has just an alpha parameter, and it does move. This one is wrong because destination is first. No, that's right. B to A. Move B to A. Threshold. Sub. I mean, I did it wrong. I mean, that one was threshold. Damn. Yeah. Completely wrong. So what I have now is already threshold, and this one is not leaky. Okay. Again, so I have mul alpha, I have move C to move A to C, I have if pose. Here we go. That was leaky. Threshold, soft sign. So soft sign will be, soft sign doesn't have parameters. Up. And it does what? It does yep, that. Then it does apps, which we don't have yet. Then it does add const 1. I'm gonna put 1 in 1. Then it does reciprocate, and it multiplies, so it's binary multiply. So we are missing apps recip. I'm gonna put them here, apps recip. So the idea is yeah, trying to get them a bit organized. Threshold, soft sign, hard switch, last one. Hard switch, so hard switch, hard switch, it doesn't have parameters. I mean, it doesn't have parameters, variable parameters, but it has fixed parameters. So we're going to put the two alpha and betas. I'm going to hardcode them because we can in the case of hard switch. In the case of hard switch, they were there. Yes, hard switch. So the values, the magic values, are alpha equals 1/6 and beta equals 0.5. So 1.1f32/6 and 0.5. Okay. So hard switch is mul alpha. Alpha is constant number 2. Add beta. Beta is constant number 3. And mean of 0. Mean with 0. 0 is constant number 0. I'm still confused by. I mean, something is missing here. At the end, we need to multiply by x the hard switch. I got it wrong, I guess, from there already. It's okay. So anyway, mean is, let's try to get it right now. Mean const of 0, max const with 1, and then we multiply by x. So I need to protect x by moving it to b, and now I can do multiply. Okay, so this one was wrong. Should I try to fix it? Yes, if I was in editor. Where is it? So where did it started being wrong? Yeah, here. So that's missing x times. Okay. Blah 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 blah. Hard switch. So here I need to preserve. So b takes a, and at the end I'm adding a multiply like that, and it should be correct. And this one is also wrong. Because yeah, same. So I'm using b a lot here, so moving x to c instead of b, and in the end I need to move back into b the preserved value that was in c to be able to multiply. So really, I mean, this form is so much nicer. There is no question about it, in my opinion. So soft sign. I have an alpha in soft sign, and the compiler is not happy with it. There is no alpha in soft sign. It put them back. Formatter really doesn't like to have them like that, like this. I mean, I can probably tell restfmt to ignore them. There is a way to do that. Rustfmt skip. Yep, I knew I used it somewhere before. So can I put it there? Is it working? Yes, it did work because the other are broken and this one was preserved. Okay, so that's, I guess it's acceptable. Up, up, up. This one is already messed up. Show vector. Okay, like that. Not like too much to mess with the default formatter, but well, I guess this is an exception. And so ops go to the line, and we have the vec like this. Well, this one is so simple. Okay, I mean, the screen is a bit tiny, so it doesn't look so bad if we have a regular width. Okay. I'm tempted to try to craft an interpreter now. So implement program, and I will have a version function compute, which will take x as f32 and return y as f32. And so I will need some registers, so A, B, C, and D. So that will be for f32. So let mut rex equals f32. So I'm doing a scalar implementation here, so no vectorization. I just want to check that the functions gives the correct results. And so I need a PC that will point to the first function, or I can actually just do it like that for op in program dot. So I need self. Of course I need self. Self.ops. And so we have a bit of work here. Op move from so dest source. And so this is a move between two registers. So I'm gonna need a 0, and we are going to return x of 0, and we need to initialize the first register to x. Okay, I want to cast this once to. Basically what I want is this. I'm not sure if this is correct, but I'm gonna try it anyway. Is it working? So can I do regs of dest equals regs of source? What is this? It's not happy. We will do something ugly for now. Yes, of course, match hope. So can I do this or not? Doesn't look too good. F32 cannot be indexed by register ID. Can I have an enumeration with Rust enumeration with numbers? Enumeration. Yeah, it's a bit low level for what I want. Well, yeah, it's a C-like enumeration. So I have yep. And then how do I use them? Bloom. Oh, just by casting. Okay. Why not? I can do that. As you size. src as you size. Okay, so we have the move. No, not yet. Not yet because yeah, I need to declare this as copy, clone, debug. What else could be useful? Let's start with these. Same for op. Copy, clone, debug, and I need a derive around them. Okie doke. Suddenly everything is red. I'm not sure why. Why it wasn't the case before. Multiple variant are never constructed. Yes, okay, that's all right. Don't worry, it's coming. Okay. I mean, come on. They are constructed by these. Yeah, because I never call the functions. No problem then. If I want to make the first one work like relu, what I actually need is max const. So let's do max const. Max const takes max const will take a constant ID and we'll do regs 0 because our language by default will act between a and a constant equals regs 0 dot max with the constant 0 and the constant 0 will be 0, but I don't have my full table of constants because what I said is in constant I'm putting 0 at 0 and 1 at 1 because I need them all the time. Gonna be dirty. I'm gonna copy. It's fine for now. Constants equals vec self.constants.clone and I'm doing, yeah, it's positively ugly. Constants dot insert at 0. I'm inserting 0 f32. And at 1, I'm inserting 1. It's fine. It's a reference implementation. It doesn't have to be efficient. Max with, so I'm targeting constants now. Constants of CST should do the trick. So now let's try to test this because we can actually test this with the function relu to start, and What I could do, actually, I think I'm going to use prop test because it's ideal for this kind of stuff. And I'm using it all the time, really. I really like this library. If you don't know about it, it's a property testing library which allows to generate random inputs, test that your function does the right thing by verifying properties on them. So in my case, the properties will be I want the reference implementation, which is max with 0, and the new implementation to return the same thing. Not sure what cargo is doing now. Okay. Did it do something? Oh, okay. So in the meantime, tracts, linalg, activations. So in the meantime, I'm going to write a couple of tests. And actually prop tests, so not a typical test. So my reference ReLU will be, so it will look something like that. I'm going to, don't remember the syntax, we will have to look it up. But it will be test ReLU, and I'm going to test for x any, I think it's like that, in any F32. So basically, I'm saying that for any x being an F32, the function, so ReLU will give me the program. So that's in definitions. I will need to make it public. So definition ReLU of x should be equal to max x and 0. So I think I have prop test assert prop test assert ec. Yep. So these two guys. Here we go. So maybe not the S here. Yep, better. So prop test is really for testing. So we'll move it to dev dependencies. And something not good, maybe something like that. Nope. Okay, let's have a look at the documentation for prop test. So I'm using prop test absolutely everywhere in Tract. I mean, specifically in the linear algebra crate, because that's how I'm testing that the matrix multiplier are correct. And as it's a big, huge bunch of unsafe code, even with actually a lot of assembly in it, that's how I test all of this without spending weeks writing, looking for corner case by hand and stuff like that. So it's really an incredible. I mean, it's both super fast once you get used to it, and it's super fast to use, and it finds stuff. It finds bugs that you missed. So it's running on the CI on a regular basis, and I think the getting started will get me started. Yep. Okay, this is what I was missing. And so once in a while, it discovers a new problem that I hadn't noticed before, a word corner case or a rounding error or something like that. and well, it's an incredible tool actually. So if I manage to get it to work. So oh yeah, it's just, I mean, the tag is just a regular test. Okay, and so it's function variable in function use that test cannot have any arguments. Let's see. Yeah, there is a macro call around the prop test, right? Prop test. The macro is here. And that's better like this. Definition is in super because I'm in a test module. Definition as an S, and max is like that in Rust. Okay, not there yet. Program doesn't implement debug. That's easy to fix. And while I am at wow, while I am at it, I'm giving it also clone, not copy because it has vectors, so it's not copy. It wants partial egg. You can have partial egg, it's fine. But now I need partial egg on up, which is okay. And if I put it there, I also need it there. Are we happy? Are we happy? No, we're not happy. Expected struct program. So super definition ReLU returns the program, and then I need to run it against the X. No, it's not run, it's compute maybe. Yeah. Okay, let's test it. Cargo. I mean, yeah, I should switch screen because you're on the partial one, and that's just not great. So let's do it like that. And then I also, I'm going to do that. Here we go. Trying to give you as much as I can in terms of space. Yep. Not too bad. Okay, cargo test. What's happening? Can't leak private type. Okay. Pub fn ReLU returns the program. Program needs to be pub. Yep. Everything needs to be pub. That's okay. Pub. Thought it was compiling. Not sure what I missed. Here we go. Hey, okay. So, I mean, at this stage, it's actually a bit suspect. So I'm going to test that it's actually working by while breaking it. So here I'm putting min instead of max, and it should fail now. And it does fail. And the good thing is, not only does it fail, but it also tells me that I mean, it reduces the test to a very simple value. I mean, in that case, the test was just one single scalar float. So, I mean, there is not much to do to reduce the problem. But if you have complicated inputs, like a big vector, when one single value is an issue, then prop test will, once it has found a problem, it will try to reduce the input as much as it can to converge to a super simple example. Just by following actually what is implied by the rules of input generation. So that's a super useful library. Anyway, it's working, and it works in the first run, which is I'm impressed actually. I think I'm going to try to get what time is it? It's 11. Yeah, I think we can try to get a couple more working. So let's make all of them public. And from there we have I mean, if they are working, then it means we have a reference implementation. And it means next time we can see how we can implement that in assembly to get, I mean, to run it in vector form and see maybe next time we can do a couple of benches, see if we are outperforming anything or terribly bad. Wouldn't presume of anything at this stage. So second candidate is affine with alpha and betas. So I'm gonna demonstrate a bit more of prop test beta in any F32, and so affine alpha and beta compute x should be, so affine I'm gonna look at my notes from before. So where was it? Affine was in, that's way too high. It was in Kali coding readme. Affine definition is alpha x plus beta. Okay, so affine should be alpha x plus beta. So I need to code for affine. I need to implement mul const and that const. Mul const and add const. Let's do this. Mul const and add const. So mul const is the same as max const, except we're doing mul. And add const is the same as mul const, except we're doing plus. Let's try it. Incredible. It's highly suspect at this stage. No, it's testing. Okay, that's just good. Next one, we've done relu, we've done affine. Following is liquirelu. So liquirelu. Test liquirelu. So liquirelu has, if I remember correctly, it just has one single parameter called alpha. It doesn't have a beta. Here we go. And it's defined by, so I'm calling liquirelu of alpha, computing x and comparing to if x is negative, then it's alpha x, else it's x. So all of these are in float for now. Okay, so well, we have at least we have an example where prop test signals a problem, and we have an explicit panic because I haven't implemented all of the operators, and so we need move. Move is done. Mul const, and we need if positive then else. Okay. If positive then else, and so definition for this was if a, which is regs 0, positive, then B, which is regs 1, else C, which is regs 2. Here we go. Nope, what's wrong? 0, F32. Nope, still no. So regs 1 expected what? Yes, I need to put the result in in A. Okay, straight. Nope. Okay, so what is wrong? So it doesn't work for negative values, for this negative value, for instance. What did I do? Let me check my leaky. Let me check first the reference implementation. So I did alpha x else x, comparing with my notes from before. Leaky if x positive. Oh no, if x positive alpha x else x. But so yeah, it's the other way around, but that's not our problem. I think I'm gonna just fix it there to be consistent, but that's probably not what's wrong here. Alpha x. Checking again. Okay, still wrong. Not big surprise. Let's look at our definition of leaky. So we're moving B to A. No, we're moving A to B. So A is X. So B is X. A is X. X. We are multiplying by constant 2, which is alpha. So we get alpha X times X, then X in B. We're moving A to C. So we get alpha X, X, and alpha X. And if alpha X is positive, then we're taking X, or else we're taking alpha X, which I think is correct. So do we have a problem here? If regs of 0 is positive, then we take A, then else we take B. No, it looks good. So let's have a look. Let's debug. Let's look at what we have in the registers. I'm going to use this one to get a more compact display because yep. Okay, leaky, show us what you're doing. So problem here is we have several attempts at running it. So what I'm usually doing when I'm using prop test is I'm splitting up tests. Once I found something wrong, I'm actually specializing the test outside of prop test. So that's inside prop test, the macro. Yep, we are outside. So that's test leaky ReLU 0. And it's no longer a prop test things. It's just, oh, I know what's wrong. I know. I'm pretty sure I know. It's because it picked a negative alpha. I mean, that's a guess, really. So minimum failing input, alpha equals 0. No. Okay, let's do it again. Let's do it then. Because we have a constraint here. Alpha must be positive, or else the alpha x change sign, and then our positive test doesn't work anymore. But I mean, it's okay. I'm not sure it's specified that alpha has to be positive, so it's a bit risky. So we can probably find a better definition, I mean a better implementation. So for instance, here I can move, I will move B again to A. So now I'm testing the right thing. Yeah, I was in the process of re-implementing a test here, but let's drop it for now. Here we go. Okay, yeah, that was enough. Okay, that was a problem. So I mean, we're going to keep this one because it's more robust, even if it does a bit more work because it moves one more value. It's so much safer that I think it's worth trouble. Next up is soft sign. No, threshold. Threshold. So threshold is the same. It has one parameter. Test threshold value. It takes an X and an alpha, and so I'm taking threshold value of alpha. I'm computing over X, and the definition, the reference implementation should be back to the README. If X bigger than alpha, then yeah, we could have also difference of behavior, because this one is actually discontinuous. So depending on the strictness of equality, we may have a bit of a discrepancy here. Anyway, if X bigger than alpha, I take X, else I take 0. Okay. So what? Yes, 0 F32. And here, so here I'm testing positive or equal, and in my here I'm testing positive or equal, so I should be okay. Nope. Okay, so minimum failing input, X equals 0, alpha equals 0, and we have test fail explicit panic. Yes, because explicit panic is this guy. There is some operator missing. Threshold, we have move, we have sub const. So add const and sub const. Can probably get rid of this later. And so sub. Here we go. Still not there. Explicit panic again. So it's threshold. We have move. We have subconst, mulconst. We have a load. Is it the first load? Yes, it's the first load. So load will take TST, which is a register, and SRC, which is a constant this time. So I will call it actually CST to be consistent. And I'm not reading in regs, I'm reading in constants of CST, like that. Okay. Nope, still nope, but panicked. Minimum failing input X is very negative, and we get an alpha, and we have a difference. We are expecting minus, we are expecting X, and we get 0. So when it's threshold, so threshold is when x is bigger than alpha, we get x, else we get 0. So what's wrong? I'm going to do something here to see what's happening. Yes, println. I'm going to do that, and we want to see, one is enough. We want to see x, and we will also show the constants in case something doesn't work. So the one which is not working, so we have an alpha of 0, which should be fine. So what is happening? We're moving x to threshold. So we're copying x to b, that's here. Then we are multiplying, then we are subtracting the constant number 2. Oh, sub 2 mul const 2. This is wrong. There is no mul. It's just the subtraction. Yes. Okay, fixed. Soft sign. Soft sign. So soft sign, I think it doesn't have any parameters. Yep. It's a simple one. Okay. Test subsign. Subsign. No alpha. And the subsign. Taking the function, computing x, and the definition was it was x over 1 plus, if I remember correctly, something like that. So definition, no subsign. No, it's not subsign, it's soft sign. And one, okay, compiler is not happy. No main function, no, that's okay. So subsign, guess we are missing some operators like apps, explicit panic, right? So we have move, we have load, apps comes after move and load, as well as recip, which I also need for this guy. So apps doesn't take any argument, and regs of 0 equals regs of 0 dot apps, and same for recip. Recip. Okie doke. Explicit panic. What am I missing? It's soft sign. Where are you? Soft sign. We have move, done, apps done, add const, recip, and mul. Yep, we haven't done the mul, the binary mul like that. So that's regs of 0 times regs 1. And in the, so it comes before the mul const, in between here. Straight? Nope. Oh, it's a rounding error. It's very close. So that's a rounding error. Where does it comes from? It's interesting actually. Why a running error? Okay. Not sure where it comes from. But I'm going to just ignore it. But I need to find a way to ignore it. I have plenty of stuff in tract to do that, but I put myself inside tract without without getting any utilities from tract because I'm physically inside it, but I didn't link anything. So I will need to. I mean, we will go some simple tests. Yeah, I guess division and receipt then multiply do not exactly run the same way for some reason. So what we are going to do in this specific case, we are going to assert that this is boring. This is floater mess. Floater always a mess. Close enough. F32, B, F32. And going to return the bool, and I'm going to steal Python NumPy float comparison. Yeah, almost equality. So usually they have this. Yep, that's what I want. Yep. So the idea is to have both a relative error and an absolute error, and you must satisfy both criteria. So yep, that's the problem with floating point. Floating point are total mess. Nope, this is not the usual definition, not with a 0 here. Yes, that's better. Airtol and Atol. Here we go. And Atol, yeah. And so we're testing that cannot find Airtol, and Atol, and I need apps and apps. It's like this. And I'm going to import use std cmp min and max. Just max. Apps de apps of A and apps of B, A.apps, B.apps. Here we go. Nope, not yet. What's wrong now? Rust. So floating points are boring, and what is specifically annoying with floating points. A bit of a pedantic, but okay. So recently there was an addition in a standard library for total order on floating point numbers matching the I3 specification, and so I'm not sure that it was extended to yeah, total CMP. That was it. I'm not sure it was extended to min and max. Okay. So instead of doing this, I'm going to do max of A F32, B F32 gives F32 if A dot partial, no, if A dot total, how is it called already? Total CMP. And there is no another way, because if I actually do this, then I will have a problem with the nans, but we will assume that we are not doing nan arithmetics in neural networks. Okay. That should do it now, and so now I can use this to test that actually what I've computed is close enough of a second expression. Close enough. Oops, network error. That's bad. Network error. Ah putain, j'ai perdu ma connexion quoi, fait chier. Okay, I'm back. I'm not sure what's happening with my connection. I've lost my only viewer. It's so sad. Anyway, I'm gonna finish this if anybody cares to watch either right now or at a different time. So the last one, the last function I need was art swish, and it doesn't have parameters, and I'm going for art swish, compute x, and the expression is of art swish. It's a bit complicated, but right there. Yep, not working. I have the weirdest problem with copy and paste. I have no two computer where it's consistent. Yep, so it's absolutely ridiculous, but I'm going to just copy it. 1 alpha times x plus beta, and I'm closing parentheses. Here we go. So alpha is 1 over 6, and beta is alpha 0.5. And so I'm going to do 0.max. So it's 0 of 32.max like this, and That's 132 dot min, like that. Okie doke. One too many. So hard switch, we have min with a constant, we have max with a constant. Let's try to remember, we have mul const, add const, min const, max const, plus a mule, and we need the move. So I think we have everything. No, we don't have the min yet. Min const. So min, here we go. Yeah, if you whoever was there before, I'm sorry for the connection. And the close enough function did work for the add sign function. So last one, hard switch. What's wrong? Minimum failing input for x being negative. The close enough function. So the problem is now we are using close enough, and we are not seeing the two values anymore. So I think, nope, that's not it. 1/6 times x. No, this I can't see any big problem there. So let's see what we are computing. Let's see, we are computing. So we are pushing, we are copying the input into the second register. That's move BA. We are multiplying by the constant 2, which is the constant 2 is alpha, so it's 1/6. And yes, we nope, that's not good. This is not good because this quantity is actually, it should be smaller and it's bigger. So something is wrong, I guess. I'm not sure what this does, so I'm gonna put parentheses in doubt. I mean, the problem is not here anyway. The problem is in the pseudo assembly side of things. So 1/6 multiplied, it should really give us, oh no, it's actually smaller because it's 35 and 34, so it looks okay. And then so we are doing a minimum with 0 and maximum with 1. It's the other way around. It's minimum with 1 and maximum with 0. Is that true? And then we multiply by x. Yes, I think so. Yes. Okay. So all the functions are working. That's actually pretty good. I didn't think I could get so far tonight. I'm going to kind of finish this by adding whatever is missing here. So we need the 5 binary ops, so that's going to be super fast. So we have apps sub, we have add sub mul min max. Min max. So add sub min mul min max. Then we have add submul min max with constants. So add submul, just need to put them in the right order. Min max with constants. So we no more need the panic because now we have full implementation. And I'm just going to put this bit of code somewhere, commit it in some branch, because I'm going to stop right there. I'm tired, and probably going to start working on. I mean, I think from there are two ways to go. The first track is to try and add whatever we need to compute the rational expression that make up the sigmoid and tanh and possibly some others. And the second pass is to go straight to assembly. Or do some benches and try to see. I mean, our current implementation would be pretty bad, but I mean, the first comparison, which is interesting, I think, is comparing like an ARMv8 implementation, for instance, on a Mac, with the Rust generated implementation. But anyway, that's yeah, I'm gonna think about it. And so next week, I mean, the plan is to keep working on that next week, probably on Monday. It's Tuesday today. So my idea was to stream on Monday, but life got in the way. So yeah, presumably follow up next Monday, same kind of hour. I'm just gonna commit this under in a branch and to keep it safe. So that's all for today. Thank you for whoever was watching. I mean, I guess there was one person who watched quite a bit, and so thank you. Bye.